Each year since 1970, leading space scientists from throughout the world have gathered in Houston at NASA's Johnson Space Center and the Lunar and Planetary Institute to exchange ideas and information. The 1979 conference marks a special observance. It is the 10th anniversary of the first Apollo landing on the moon. In the space sciences, where it is common to deal with eons and millennia, 10 years is a mere blink of the eye. Yet in that brief span, those here today have witnessed almost total upheaval in their respective scientific fields. To say that we have undergone a revolution in lunar and planetary science is more than just rhetoric, when you consider how far we've come in a single decade. Before the Apollo era, scientists who wanted to learn more about the formation and evolution of the solar system didn't have much to work with. From the entire solar system, they had only two sources of materials available for direct analysis: meteorites that had fallen to Earth from outer space, and of course the rocks and soils of Earth. But the dynamic nature of the Earth has resulted in the processing and reprocessing of its rocks and soils for hundreds of millions of years, totally destroying its early geological record. As a result, an Earth rock more than 3 billion years old is a rare find even today. Most Earth materials are far younger. But meteorites that have fallen to Earth were found to be extremely old. The oldest, about 4.6 billion years, and most scientists believe that was near the time the solar system formed. So between the ages of Earth rocks and meteorites, there was at the time a gap of 1.5 billion years, a period totally erased from the Earth. Long before the Apollo era, the idea that perhaps knowing the moon would lead to a better understanding of Earth and the solar system had occurred to many investigators. And with the telescope, they studied its every surface feature. They charted the dominant light-shaded areas, the highlands, pitted and scarred from eons of meteoroid impacts, and the smooth, dark basins that Galileo in the early 17th century had called the Maria, or lunar seas. They were able to calculate the height of lunar mountains, some of which rise 5 kilometers above the terrain. They knew the length of ancient scarps or faults which may slice across the moon's face for 100 or more kilometers. From pole to pole, they studied craters, older ones with outlines barely visible, newer ones with streaks of displaced rubble radiating out from their centers, craters overlying craters, and craters within craters. Scientists thus came to know the moon's surface features in minute detail. Yet beyond what they saw, they could only speculate about its origin, its age, its chemical composition, its structure, and about what processes had shaped it in the past. There was no shortage of theories, but there were very few facts. By the late 1950s, improved technology in the form of automated spacecraft gave us a new perspective of the moon. These unmanned probes from both the Soviet Union and the United States sent back images never before seen by the telescope, including the first views of the moon's backside. From surveyor spacecraft that soft landed on the surface, there were even some basic data on the nature and chemistry of lunar surface materials. Here, too, was the first concrete proof that landing craft and astronauts would not sink from sight in the powdery lunar dust. Yet for all the centuries of telescopic study, and more recently the flurry of automated moon probes, the detailed analysis of Earth materials and meteorites, in spite of all that was accomplished, prior to the Apollo program, we knew next to nothing about the history, composition, and structure of the moon. Extremely different views were held by eminent scientists the world over. Theories and opinions snowballed, and in the absence of facts, they clashed head-on. Unless we could obtain pieces of the moon for study and analysis, understanding it would remain an impossible dream.
4, 3, 2, 1, 0. All engine running. Liftoff. We have a liftoff. 32 minutes past the hour. Liftoff on Apollo 11. Tower clear.
Eagle, you're looking great. Coming up 9
On
minutes.
July 20th, 1969, the dream became reality.
60 seconds. Lights on. Forward. Forward. Good. 40 feet down, 2.5. Picking up some dust. 30 feet, 2.5 down. Straight shadow. 4 forward. 4 forward. Drifting to the right a little. 20. Down a half. 30 seconds. Forward. Just. Good. Okay. Contact light. Okay, engine stop. We copy you down, Eagle. Houston, Tranquility Base here. The Eagle has landed. Roger, Tranquility. We copy you on the ground.
After years of planning, the detailed on-site exploration of the moon had begun. And briefly, the world stopped as people everywhere shared this greatest of moments. Even scientists, who had spent years preparing for this day, were awestruck by the sights and sounds from the moon. Making the most of their brief time on the surface, the astronauts set up a small science station to return data back to Earth. It was the forerunner of other stations erected on later missions. It was this network that would allow scientists to keep track of the moon's geologic behavior for several years. Tranquility Base presented the Apollo 11 crew with an assortment of rocks and soils. Most of it appeared to be basaltic rock, the most common form of volcanic lava. Whether or not there had ever been volcanic eruptions on the moon had been one of the major pre-Apollo debates. Now, within minutes after the crew stepped onto the lunar surface, it was no longer an issue. But quick and easy answers would be the exception. Most discoveries about the moon would have to be built piece by piece from tiny fragments of information during the many months of painstaking work that lay ahead. When Apollo 11 returned to Earth, a carefully developed program of lunar samples investigation was set in motion. Geologists, physicists, chemists, biologists, several hundred scientists from here and abroad had pooled their talents for the task at hand. Although investigators worked with the same types of samples, they looked for different things. Some groups measured ages and chemical compositions. Others worked on the chemistry of minerals and their atomic structure, while some experimented, defining the properties of lunar rocks and soils. But not all of the investigators worked with samples. Some of them read electronic blips and tracings, the signals coming from the geophysical instruments of the Lunar Science Station. Here, a running account of the moon's internal activity, the basis for determining its structure, would be recorded and deciphered for the next several years. the techniques and procedures for investigating the moon were working, and working well. The goal now was continued exploration to obtain a variety of lunar materials from different geological terrain and to establish a network of scientific stations. Over the next 3.5 years, Apollo 11 was followed by 5 more lunar landings. All of the landing sites were near the lunar equator on the Earth-facing side.
17 Houston,
From first mission to last, the scientific gain grew steadily. A big factor was the lunar rover, used on the last 3 missions. With this new mobility, crewmen ranged further from home base, and along with modifications to the lunar module and the spacesuit, they were able to stay longer at the exploration site.
Okay, I copy that.
On the final mission, astronauts could extend their total exploration time to 75 hours. Quite a contrast to the 2.5 hours of Apollo 11. More and better measurements were also transmitted from the lunar science stations, which grew steadily in size and sophistication. Sample collecting, too, became more selective and better documented on the later missions. And for the first time, on Apollo 17, a geologist was a member of the crew.
Oh, hey, there is orange soil. Well, don't move it till I see it. It's all over. Orange.
On December 14, 1972, the last Apollo crew lifted from the lunar surface, and with them, the exploratory phase of Apollo came to an end. But the scientific phase, which by then was well into its 3rd year, had already answered many of the major questions about the moon. The story that began to emerge told of a moon far more interesting and complex than ever anticipated. For one thing, moon rocks were found to be very old, falling in a range from about 3 billion to well over 4 billion years. Significantly, moon rock ages began about where the ages of the oldest preserved Earth rocks left off. So in learning about the moon's past, scientists were also filling in pieces of the missing history of the Earth. No new chemical elements were discovered, but there were minerals that scientists had not seen before. The moon was found to have no free oxygen, no water, and no trace of life, present or past. Seismic activity inside the moon was found to be extremely weak, only about 1/10,000,000th of the activity inside the Earth. Except for the impact of small meteoroids and the steady stream of atomic particles from the sun, the moon explored by the astronauts had been quiet and inactive for the last 3 billion years. But the investigation showed it was not always so calm. Rocks from the lunar highlands revealed an extremely violent beginning. Almost 4.5 billion years ago, shortly after the moon had formed, its entire outer shell was a seething ocean of molten rock, melting to a depth of from 100 to 300 kilometers. During the next 100 million years, it began to cool, and the outer shell began to solidify. Minerals began to crystallize. High-density minerals tended to sink. Low-density minerals floated to the top. When cooling and solidification were complete, these new distributions of minerals had formed the separate layers of crust, mantle, and core. This process caught a lot of scientists by surprise. Melting and separation into layers had never been proposed for the moon. What's left of the early lunar crust after being torn apart by meteoroids, is the light-colored material we now call the highlands. But even as it formed, meteoroids were pounding it to bits. Scientists are not sure about the frequency or the intensity of cratering during the next billion years. However, they are certain that about 4 billion years ago, the devastation reached a peak. The clues were found in a class of samples called breccias, which are made up of fragments of different rocks, all broken and welded together by heat, some containing tiny spheres of glass. With breccias consistently showing age imprints centered around 4 billion years, the evidence was compelling. At that time, the lunar surface must have been bombarded and broken up on a massive scale. A population of extremely large bodies, some as much as 50 kilometers across, smashed into the moon. They blasted the crust apart and gouged out the giant Mare basins. The largest of the basins, Mare Imbrium, is big enough to accommodate most of Western Europe. The barrage on the moon was so intense that most likely the Earth received a simultaneous pounding. Probably the whole inner solar system was teeming with the leftovers of formation, the loose debris that had not been collected into planets. After this major cataclysm, the cratering rate began to subside, and the solar system rapidly became a fairly clean place. By now, the moon, the Earth, and the other planets had swept up most of the loose debris. The next stage of lunar history was recorded in the basaltic lavas recovered from the Mare basins. Some 100 million years after the heavy bombardment ended, heat from decay of radioactive elements began to build up inside the moon, eventually getting hot enough to melt the rocky material. In time, as the melting spread, the accumulated lavas were forced upward through faults and fissures to the surface, where they began to fill the large basins. Filling the basins, forming the lunar maria, much as they now appear, was not, however, the result of a single rampaging lava flow. Age dating showed that lava was extruded intermittently, in one place or another, for almost 1 billion years, from 3.9 to 3 billion years ago. After that, the moon settled down to a quieter existence, and has remained essentially the same to the present day. Among the subtle changes which have continued on the moon is solar wind bombardment, the steady flow of atomic particles streaming outward from the sun. Particles striking the moon many millions of years ago left their evidence embedded in lunar materials, and these can be detected today. This scanning electron microscope, for example, is studying the tracks left by solar particles as they pass through a lunar sample. By making such precise measurements, scientists are able to construct a long-term history of the sun's activity. The surprising result is that the sun has been a fairly well-behaved star for many millions of years. There were no noticeable sun deviations even during the ice ages of Earth, a finding that tends to weaken theories that link Earth's climate with luminosity of the sun. The samples did not completely satisfy a major pre-Apollo enigma: how the moon originated. Processing of the lunar materials by melting of the outer shell, meteoroid bombardment, and the long volcanic phase destroyed all traces of the moon's primitive starting material. However, investigators have recently discovered certain Earth-Moon chemical similarities that can be explained only if they originated in the same neighborhood. But the mechanism of origin could have happened any of 3 ways. the moon could have been torn from the primitive Earth and captured in its present orbit. The moon at Earth could have accreted from particles in the same vicinity at the same time. Or the moon could have condensed out of an early primitive atmosphere surrounding Earth. Lunar origin remains an open question that will not be easily solved. Before the Apollo program, scientists were struck by the differences in the Earth and Moon. Many believed the Moon was a solid homogeneous sphere, related more to primitive meteorites than it was to the planets. But after analyzing lunar materials, seeing the patterns of chemical elements, the minerals that had formed from these elements, and the arrangements of these minerals in rocks, they came to realize that the Moon had all the earmarks of an evolved planet with a history all its own. The difference, they found, was in the separate paths of evolution the Earth and Moon have taken, primarily the result of their different sizes and starting conditions. If the Earth and Moon formed near each other, they probably started out with a similar mixture of elements, such as aluminum, silicon, and oxygen. Like the Moon, the Earth probably experienced an early melting phase that resulted in its separation into layers. The heavy bombardment phase discovered on the Moon must have been sustained equally by the Earth. But during the phase of internal melting and volcanism, their common ancestry began to diverge in a way that would set them apart forever. For one thing, the Moon, being smaller, had a lesser share of radioactive elements than the Earth. And these are the elements that, in decaying, generate heat. Also, the heat that was produced was lost more rapidly, simply because the smaller the body, the faster it loses heat. The larger Earth, with a larger store of heat-making elements, and the potential to hold heat longer, developed a massive molten iron core that would help keep our planet running, as it does now, for billions of years. The intense heat powers volcanoes, recycling rocky materials to continually produce new crust at the surface. Heat from radioactive decay also created a narrow zone of molten rock just below the crust. It acts as a sort of lubricant, allowing the crust to shift about as thin plates. It is these lateral plate movements that have given the Earth its wide variety of changing surface features. The Moon, with a crust so thick and rigid, never experienced lateral plate movement. Its mountains, which tend to lie in rings on the periphery of the large basins, were built from materials displaced from the basins when they were formed by impact. Nor were lunar rills formed by crustal shifting or by the cutting action of water, as they often are on Earth. Scientists believe they are old lava tubes that have collapsed over the last 3 billion years. At the time the Moon was losing heat, it was also losing its volcanic gases. And it is from such gases that atmospheres form. But with a weak gravitational field, again the result of size, the Moon was unable to retain even the heaviest gases. Earth's gravity held most of its gases, gases that eventually formed a primitive atmosphere. And from that atmosphere came torrents of rain for millions of years. The basins were filled, and the Earth had oceans and seas, lakes and rivers. And from the water, life itself would eventually arise. The moon, with no chance of forming an atmosphere, could not develop even the lowest forms of life. It was just too small to make it. After about 1.5 billion years, it reached the terminal phase of its relatively short evolution. The story of the moon is still not complete. Although its historical outline, once it formed, has been firmly established, its basic structure and chemistry have been determined, many questions remain. Only about 10% of the samples returned by Apollo astronauts have been investigated in detail thus far, so a lot of work lies ahead. Deciphering the complex breccias and core samples is slow and tedious work, but it is here that extremely complicated measurements are now being made. Measurements aimed at uncovering facts about the moon's origin, its first 100 million years, its volcanic history, and more about the history of the sun. When will we return to the moon? No one can say for sure, but certainly it has a role to play in the future. For a science colony, its location, the lack of a distorting atmosphere, make it a natural choice. As a staging base, the moon may someday launch exploratory missions to the planets and beyond. The moon is also a potential mining site for extraction of its abundant storehouse of metals, aluminum, titanium, calcium, iron, raw materials that could be used for building large-scale structures in space. Today, after 10 years of lunar and planetary investigations, interest and momentum continue to grow. The lessons learned from the moon are being applied to the Earth and to the other planets, especially nearby Venus, Mercury, and Mars. The processes observed on these planets are as strange as ever, but no longer are they mysterious. Scientists see them as extensions of patterns which are now familiar. And in time, they will understand their structure, their evolution, how they relate to Earth, and eventually, how this solar system of ours came to be. Apollo was much more than a triumph of technology. Like Columbus' voyage to the New World, the Wright brothers' flights at Kitty Hawk, the Apollo missions to the moon mark a major turning point in human history. Apollo was the first step in a journey that will never end.